Thank you, Ian, and thank you to SPS for organizing this evening's event. There. Okay. Everyone can see what I've got up there?
Yes.
Great. So my area of research is experimental nuclear physics. So, and in particular, it's intermediate energy photonuclear physics. So this is a set of experiments that use high energy gamma rays or photons to probe both the structure of the nucleus and the properties of the nuclear force through experimental measurements. So the research I do, the energy of these gamma rays is less than around 300 MeV. Intermediate energy keeps changing as particle accelerators get bigger. But 300 MeV is interesting because it includes what's known as the pion photoproduction threshold. That's around 135 MeV. And I'll explain in a bit why pion photoproduction is an interesting process to study. So these photons will interact through the nucleus through the electromagnetic force. Photons do not have a nuclear force associated with it. So this is advantageous because we avoid all the complications that come with having a nuclear force interaction in the initial state. All we have to worry about is the nuclear force in the final state. Another advantage is because gamma rays are electrically neutral, they can penetrate the entire nuclear volume. And they don't just interact with the nucleons on the surface, as we would see if we used a proton or a neutron or some other nucleus as the probe in these experiments. So I'm involved or have been involved in multiple types of experiments. One of these is the study of Threebody systems, the A=3 system, helium-3 and hydrogen-3 or tritium. They're both very interesting. There's also the study of what's called nuclear Compton scattering. Many of you will have seen Compton scattering in atomic systems. Well, we can do exactly the same thing where the scattering takes place off the nucleus rather than the atom. And as I mentioned earlier, pion photoproduction is another area of research. So if we look at these few nucleon systems, helium-3, 2 protons, 1 neutron. Tritium is the reverse, a single proton with 2 neutrons. So if we look at how these 2 atoms break up, or 2 nuclei, I should say, break up, that gives us information about how the forces between the proton and the neutron might differ. And even more intriguingly, it's a way we can study what are known as three-body forces. And this is a class of force that exists between 3 bodies. It's not a combination of 2-body forces when there are 3 atoms or 3 nuclei in the system, but it's a force that exists between the 3 bodies itself. So it's a very small few percent effect, but different theories make calculations about it. And to test those theories, we need very precise measurements. And so that's some of the work I've been involved with. Compton scattering, this sort of talks about how the proton or the neutron, the nucleon we call them, is distorted by the electric field associated with the gamma ray. It's really a polarization of the internal structure of the proton or the neutron, in other words, the quarks. So again, we compare the measurements with the predictions from various quark-based models, and it gives us a way to test these different theories. And finally, pion photoproduction. This is fascinating because it's one of the very few low energy processes where it's possible to actually create QCD-based theory. Most QCD theories, we have something called containment or confinement, where basically it says the quarks are contained in the proton and the nucleus, and you can never separate them. And so it's very difficult to make measurements or theories except at very, very high energies. Pion photoproduction gives us a way to do it at low energies. And when we make a pion, we've got a direct rearrangement of the quarks in the nucleus. And so again, we compare these measurements with predictions from different models to say something about the model. So here's a little cartoon of what's going on. A proton is made up of 2 up and a down quark. If we take a photon and produce a pion, in the case of a positive pion, it's made of an up and a down bar. So I've rearranged, me pointing at the screen doesn't help. I always do that. So we can rearrange the quarks inside the proton to make an up and two downs a neutron on this up-down bar. And so again, we're directly interacting with the quarks, so we can compare with the predictions of theory. So these are low energy theorems, things called dispersion relations, chiral perturbation theory. This is one of those quark-based low energy theorems. There are partial wave analyses of existing data that can be used to make predictions. And again, all of the goal here is to make measurements that we can compare. So this chiral perturbation theory, chi-PT, we can predict the different orbital angular momenta contributions that go into pion photoproduction compared with experiment. So the projects that we have is there's existing data that can be analyzed. This is from measurements that were done at MaxLab in Sweden. This makes use of the CERN's data analysis package called ROOT. There's also simulations of the measurements that need to be made in order to correct to the data for the loss of particles from the detectors, things like that. And there's a possibility of developing new experiments at the Higgs facility, the high intensity gamma ray source that exists at Duke University. Okay, so thank you everyone. If there are any questions, I'm more than happy to answer them.